Hey everybody, thanks for tuning in. I'm Johan Wenzel and I'm going to be presenting Improving Virtual Reality Ergonomics through Reach-Bounded Nonlinear Input Amplification. I did this with my friend Greg and my advisor Dan, and let's just jump right into it. So, one of the fundamental open problems with virtual reality is the mismatch between the physical and the virtual. This was a problem with motion control technologies like the Wii, as well as the Kinect that has you jumping around your room, and now once again with VR. So movement can be challenging in applications like this due to mobility requirements, fatigue, or even just having too small of a play area. In many cases, the user's physical body can get in the way, either through health restrictions or even just bumping into things. Shocker for the day, motion controls are always going to need some amount of motion to work, and as such we need to compensate either in our spaces or in our movement techniques. So a typical remedy to this is input amplification, in which smaller, more comfortable movements are transformed into the larger, more dramatic movements. Previous work suggests that the maximum of the real and the VR hands should differ is roughly 20% of the user's arm length to preserve immersion. This presents an opportunity to prioritize increased comfort while still maintaining immersion. So here's a preview of our technique that proposes a few fixes to this. It amplifies the user's motion along a smooth, non-linear curve, which allows us to make reaching in VR more comfortable while still keeping the user's sense of body ownership. So previous work for this falls into two camps: target-dependent and target-independent techniques. Target-independent techniques often increase comfort at the expense of body ownership, while target-dependent techniques maintain body ownership but aren't applicable to larger varieties of tasks. This presents a unique opportunity to create a technique that provides both the comfort benefits of target-independent techniques as well as the body ownership focus of target-dependent techniques. I'll get more into detail about these techniques next. So, first category of input amplification is target-independent techniques. The classical example is the go-go technique, which was presented in 1996 and is a two-part scaling algorithm. The first two-thirds of the user's reach functions normally, but then the remaining one-third is amplified exponentially. Next is Lee et al., who tested 4 different methods: no offset, which is regular motion; a linear offset, which is uniformly amplifying user motion; a fixed length offset, which is a constant offset, so users' hands were always more forward than they usually are; and then the go-go technique. They found that no offset is best when targets are in reach, and linear is best when targets are beyond reach. So these two techniques help the user move more comfortably. However, their implementations risk breaking the user's body ownership and thus reducing the user's feeling of immersion in the VR scene. We also have more ownership-friendly techniques in the related work. The first is OwnerShift, which explored the interaction between hand amplification offsets and body ownership in VR using a virtual panel UI. So a key insight here is that gradual adjustment helps people not notice when you mess with their proprioception. Then we have Ergo, which created offsets more dynamically by segmenting the entirety of the user's reachable space into tetrahedrons, with the vertices of the tetrahedrons aligned with targets in the scene. As the user moved their hands between the tetrahedrons, the system would use optimization functions and simulated annealing to calculate the most ergonomic way to get to the intended target. Ergo significantly improved ergonomics with improvements of up to 7.2%. This work, while being implicitly designed to maintain the user's comfort while still amplifying the user's reach, seems to be the closest related work, and as such, our first experiment compares our experiment to Ergo. So both of these still need target positions in the scene to function. This makes them non-optimal for general use, as there are lots of applications that do not have targets in the scene, like painting or 3D modeling. We introduce a new input amplification method called Reach-Bounded Nonlinear, or RNL, input amplification. This technique allows for more comfortable reaching movements, and unlike other methods, it does not reduce body ownership, and as well, it does not require targets to function. And the kicker here, some users may not even notice it happening. So here's the technique demoed again. Notice that the VR and the real hands meet when the user extends their hand out fully and when it's back at their neutral point. How this works is that the computer infers the shoulder position, PS, the user calibrates their neutral resting point, PN, and their maximum reach, Pmax. Pmax defines a theoretical sphere of maximum reach around the user's body for that arm. Offsets are based on the neutral position and the controller's current position, which is turned into P star H, or the amplified point. So the computer gets the physical offset R from all of the points and uses R into an amplification function to calculate that new offset for P star H. This is what the calibration process looks like. They select a neutral, comfortable point near their body, and then they reach out as far as they can. So we did a pilot study with 5 people to rapidly assess what amplification curves should look like. We learned 2 things. So first is, curves need to be kept smooth to avoid discontinuities. Discontinuities or sudden changes in slope can cause the VR hand to jump instantly from one spot to another, breaking body ownership. And the next one was to prioritize a slope that is greater than 1. Slope less than 1 makes the VR hand move more slowly than the real hand, which ended up feeling really unpleasant and immediately broke body ownership. So here's what the amplification curves we developed as a result. So the first task worked like this. The user would begin by tapping the cube placed at their neutral point. They would then tap the 2 spheres highlighted in green. So we have 3 task layouts for this experiment. So the ergonomic layout places targets easily within arm's reach, which is 21% of their arm span away. The limits layout places targets at a fixed position at the limits of the user's reach, so 44% arm span away. And then the fixed layout places target at a position fixed in the world, so the user has to walk around. This is not centered to their shoulder like the previous layouts. And then target layouts all came from Ergo for a meta comparison. So for experiment 1, we have one objective. Does RNL perform similarly to Ergo? We have 3 amplification levels based on the 3 curves: none, no movement; low, which is a little bit of amplification; and high, which is more dramatic amplification. We have our 3 target layouts that I mentioned. We have our 30 trials, and we have 18 participants who ran the experiment. So for results for experiment 1. First off, for time to complete, we found no significant difference between any of the 3, so amplification didn't really make a difference. Next up, we measured their comfort. So we measured comfort using what's called the Rapid Upper Limb Assessment, or RULA. So RULA works by checking the angles of the user's shoulder, the user's elbow, and the user's wrist, giving an ergonomic score based on that. So from that measurement system, we found significant differences in the limits and the fixed layouts for both amplification styles. So there was a significant reduction in user discomfort based on this. Next up was physical path length. So this is just how much they are physically moving. We found that in all layouts, we reduced physical path length. So they were moving much less. So next is virtual path length. We found that we did also increase virtual path length in all layouts, suggesting that we're potentially overshooting in their movements thanks to the amplification. And next we ran a survey based on different questions for comfort, ease of reach, overstretching, sense of control, and body ownership. We found that in high amplification, the body ownership was generally lower than with none. This might suggest that high amplification can cause offsets that are near the recommended max limits, but 5.22 is still promising since it's still a relatively high score from 1 to 7. So, main takeaways from experiment 1. We found that the technique works as well as Ergo, the state-of-the-art. It significantly improves comfort by reducing RULA scores, and it does not significantly affect task completion speed. There were some significant costs to path length, meaning that their virtual hand, not their physical hand, moved more. But this raises a question. What about the in-between curves? So this naturally prompts experiment 2. So let's push this further. We're now looking for a gradual picture of amplification. How much can we amplify movements before some of the adverse effects that we saw in experiment 1 start happening? So let's test more gradual changes in amplification, as well as pushing amplification even further. So this was the task for experiment 2. Participants would click back and forth between a sphere at their comfortable point and a target somewhere in the space. So neutral point, target, neutral point, target. There were 3 layouts. There were the close body layout, the mid-range layout, and the far layout. I'll get more into those task layouts. So instead of 3 curves, we're now testing 10 different curves, making amplifications from 0% to 45% of the user's arm reach. So here are the layouts of targets in experiment 2. So purple targets were close to the user's body, blue were mid-range, and green were at their maximum reach, so close, mid, and far. So for our design, we had 10 amplification levels. That's the 10 curves, 5 blocks, 3 distances, near, mid, and far, 5 target positions at each distance, and we had 18 participants running the experiment. So for results, we found significant results for time. So mid-range targets had significantly worse times by amplification 6, and far targets became significantly worse at amplification 8. So this did cause users to take a little bit more time to select the targets. Next up is comfort, using Rula again. So comfort differences became significant at amplification 5 for close targets, amplification 4 for mid targets, and users were more comfortable at amplification 2 for far targets, meaning that the farther targets were away, the more that amplification benefits became apparent. So next, for error, there was no real trend in the data for error based on amplification, other than 2 small significant areas, which was amplification 2 for mid-range targets and amplification 8 for far targets. We found that for input amplification, significantly reduced physical movement for all target distances. So amp 1 for close, and then 2 and 3 for far. So however, it significantly increased virtual path lengths at all distances, with mid targets feeling it the most. Check out that difference in slope. So mid targets had a way higher trend for virtual path ratio as people were going on. Next up, we ran surveys about each amplification level without outright telling them that input amplification was happening. So first, there was no statistically significant results. However, we can still point at some interesting possible trends. So for the first chart, we found the affect started to get worse around amplification level 4, suggesting that they started to enjoy the task less once amplification got too strong. Where our next question asked them if they felt like they had a doubling of hands. The trend here was fairly constant, with a small worsening after amplification 4. Note that this legend is flipped. The good answer is to disagree, because they had 2 of the same hand here. Next up was that this was one of the main body ownership questions, and this results suggested that things got a little less convincing around amplification 4. This lines up with previous findings. Amplification 4 is a boost of 20% of the user's arm reach, which lines up to the previously established limits for body ownership. So then there were similar results for control. Things started to decline around amplification 4, so users start feeling like they had less control as amplification got more strong. So next up, we noticed that if people were going to notice amplification, they noticed by amplification 5. We asked users in the introductory study how often they play 3D video games. From this, we found a Spearman's rank correlation of -0.48, suggesting that people who regularly play video games notice amplification earlier than those who don't. So, main takeaways from experiment 2. Amplification strength and target distance both affect the usability. Amplification strength improves the comfort even in small amounts, and then the results suggest that enjoyment and body ownership both decline roughly around 20% of the user's arm reach. Let's get into some of the design recommendations. So first off, designers should consider what they'll have VR users be doing throughout their application. Will they be reaching more? Consider amplifying their movements. Do they require more precision at the mid-range of their reach? Consider not amplifying as much, since it'll be less accurate. Do they need a high level of body ownership? Consider their movements only amplifying up to 20% of their arm's length, since that's a typical breaking point suggested by both the related work and our study. Next up, consider the function. So hand offset is super important here. The separation between the real and the virtual hand can break body ownership if it's larger than 20% of arm's reach, and can reduce task performance past 30%. Slope is a big issue here. It determines the relative speed of the virtual hand compared to the real hand. Moving too slowly can feel immediately bad, while moving too fast can break body ownership. Task performance declined around 30% of arm's reach in our experiment at a maximum slope of 1.92, which is nearly double the real hand speed. Discontinuities are also important to consider. We kept our curves smooth to make sure that the virtual hand doesn't instantly jump from one place to the next. Our pilot studies showed that this was a dead giveaway. So lastly, consider the person. Gaming makes people notice amplification much more quickly. Tailor your amplification to your intended audience. So, to summarize, reach-bounded nonlinear input can help users use VR more comfortably without changing their levels of immersion. We hope that these results can help future designers and researchers develop more comfortable VR applications. Thanks for watching.